Welcome to Maths and Science with Mrs. R. So, today we're going to be dealing with electric circuits. So, just a disclaimer, I'm going to be teaching in English, however, nditira code switcher to prevent a bit for better understanding and utarcheza queen for you all to understand. And also, don't forget to like, subscribe, and share. So, let's dive right into it. So, electric circuits, you've been doing them since primary school. So, you know that it's made out of individual components that are connected together to allow for the charges to flow. So, the components, we're going to be talking about the conducting wire, the battery, the switch, the resistor, the ammeter, and the voltmeter. So, we're going to talk about them one by one. So, let's start with the conducting wire. So, your conducting wire is there to provide a pathway for your charges to flow. So the conducting wire is made out of charges. So which charges are this? The charges are the charges that we have learned about over mrao with atoms, the positive charge and the negative charge. However, charges in a mover, the charges that move are the electrons. So meaning that whenever we talk about the flow of charge, we're going to be talking about electrons that are flowing inside the conductor. Then the charges in a conductor don't just flow. So meaning that in a circuit, charge ziba from the conductor, not from the battery. So the battery does not supply charges to the circuit. However, the charges are already there, conducting wire. So what does the battery do? The battery only provides energy. It provides energy for the charges to now move. So for you to have charges moving, there should be a battery or a source of energy which is connected to your conductor. So in our case, it's going to be a battery. So what does the battery do? It provides energy for the charges to flow, meaning that if there is no supply of energy, the charges move. Then the moment you plug in a battery, then they will start moving. And then next up, we have a switch. So a switch is the one which controls the flow of charge. So a switch ringatangana nayo in two instances. So you can come across an open switch like that one. So with an open switch like this one, there won't be any flow of charge. There won't be any flow of charge. There will be no flow of charge. And if you find your switch closed like that, then there will be a flow of charge. Why? Because if your charges are maybe flowing from this direction, when they reach this point right here, there's going to be a gap. And remember, charges can't fly. So ngauri charges zifupi zidodaza soko imane padzarindera for the path to be closed. So the moment your path is closed like that, your charges now can flow. So meaning that for you to have charges flowing, you should have a closed switch. And then if you want to break your circuit or if you want the charges to stop flowing, you can open your switch. And then moving on, we have what we call a resistor. So a resistor is there to oppose the flow of charge. It is there to oppose the flow of charge. So now I'm going to draw all these components all together, and then I'm gonna show you how the charges flow from which direction to which direction. So right now I'm drawing the battery, and then after the battery there is a switch. We spoke about a switch. So there is your switch, which is a closed switch, and then you have a box there. That box is symbolizing a resistor, and then we close up our circuit like that. So as we had said, the components are connected together like that for you to have charges flowing. But an important thing, there should not be gaps in between your circuit such that charges azingadokonwanandira your move. Ikotiba closed for you to have current or for you to have a flow of charges. And then next up we have what we call an ammeter. we have an ammeter. So what does an ammeter do? An ammeter is there to measure current. So because your ammeter is there to measure current, it means that it should be along the pathway henepa ka circuit ya borine. It's gonna be like that. Let me just include it there in the drawing. So you have an ammeter connected like that. So how does your current work? So actually, what is current? So current, it is the rate of flow of charge. The rate of flow of charge. So the moment you see rate, you see there is time somewhere in between there. So when you say that your current is the rate of flow of charge, rate means that time is dividing. Somewhere there is time at the bottom as the denominator. So your current is equal to the charge over the time, meaning that this is the rate of flow of charge. So your charges flow in a conventional direction. The conventional direction for the current is from the positive terminal to the negative terminal. So your current flows in that manner, and it makes a cycle like that from the positive terminal to the negative terminal. And then when we said that the ammeter is there to measure current, the other question would be, but then aren't the charges going to get tired? Aren't they going to use up their energy as they are passing through the ammeter? And then the answer is no, they won't use any energy. They won't use up any energy. So the ammeter, it has negligible resistance. This is the most important part. An ammeter has negligible resistance. So remember the resistance ya hone ya neglect yanga ayiwo, meaning that charges zasho, as they are passing through here, they won't experience any opposition as opposed to when they are passing through a resistor. So as we said about the resistor ya borine is there to oppose the flow of charges. So meaning that your charges are gonna flow here. The moment they reach the resistor, because they're experiencing opposition, kana dziko experience an obstacle. So I like to say that the resistor is like an obstacle along the way. And then I always make an analogy of the charges being like little soldiers. So from the positive terminal, your soldiers are busy running. They got energy now. They are running there. And then when they get to R, it's like an obstacle along the way. So when they get to an obstacle, they need to use up all the energy that they have to pass through that obstacle, or as azingapir. Meaning that if they now need to pass through this resistor and they need to use up energy, we need to know how much energy was used up by those charges as they were passing through that resistor. So this is where we introduce a voltmeter. We need to connect a voltmeter across the resistor. It is always connected parallel to the resistor. We can also put one up here to measure how much energy was provided by the battery comparing to how much energy was used up there by the resistor. If we were to connect one also here across the ammeter, we are going to find that the voltage used up is 0. Because why? No energy is used up here by the ammeter, because it has negligible resistance. Always remember that. So then, as I was still saying, so your current as it flows here. Now the other question is, but there is now another pathway, the green one here. Isn't and other charges going to diverge now and take this path to avoid the resistor there? No, guys, it's even worse down here. It's even worse. The voltage, the voltmeter is connected in such a way that it has very, very high resistance, meaning that all the charges that are coming in this way, they're gonna prefer to just go through the resistor and not take the other path. Why? Because the obstacle here is too big. So for example, as I was still saying, the resistance is very high. obstacle you're gonna avoid it. As long as the other path still gets you to where you're supposed to go, you definitely gonna avoid it. Meaning that also our charges, they won't go through V, they're just gonna go through R. So whenever you see kasekete wuna V, just know that no current was ever diverged to that path, it just went through the resistor. Okay, so then that is how your current is going to go. Is gonna pass through the resistor, which has manageable resistance, so the obstacle is reasonable, you understand. Then at A, there is no resistance, meaning that they are cruising nicely. When they get to R, there's a problem now. They need to use up the energy, which we're gonna calculate here by the voltmeter. What are we calculating? We are measuring the potential energy. The potential difference. What is the potential difference? Potential difference is the energy transferred by the battery per unit positive charge. Energy transferred by the battery. Meaning that we are measuring the energy given to each charge for it to start running around here. Provided by the battery. So what is the unit for potential difference? It is measured in volts, which is V. And then with current, it's amperes, which is A. So, as I was still saying, the potential difference is the energy per unit positive charge. The moment you see per unit positive charge, per unit electric charge, you know that if it says per, means that whatever we're talking about now is going to the denominator, meaning that the voltage is going to be equal to the energy, which we're going to represent by W. Other definitions says that it's work done. The work done. So W over Q. So your charge is in coulomb, and then your energy in joules. Then V is your potential difference, which is V. So that is it about the potential difference. So just a summary, let's talk about the circuit again. Your circuit has a battery. A battery is there to provide energy, right? Energy to what? To the charges to flow. And as the charges are flowing, we can measure the rate of the flow of those charges using an ammeter. And then as they flow, they're going to flow through a closed switch. If the switch was open, they were not going to flow through it. So they're going to go through the closed switch and through the resistor. They won't go to the voltmeter because it has very high resistance. And then they're going to go back to the negative terminal. And then we have resistance. Resistance is the ratio of the potential difference across a resistor to the current in the resistor. So this is where you get your formula, which says that R is equal to V over I. So your V is the potential difference, PD, which is your potential difference, and I is your current. And then what is R? R is the resistance, which is measured in what? In ohms. So this is the symbol for, or the unit for resistance is ohm, like that. So then resistors can be connected in different ways. Your resistors can be connected in a series circuit, or they can be connected in a parallel circuit. So the series one is like this one, is this one, then the parallel one is that one. So stay tuned for the next video where we're going to talk about the difference between the series circuit and the parallel circuit. But for now, all you need to remember is that with the series circuit, there is only one pathway for the current to flow. And then with the parallel circuit, there is more than one pathway for the current to flow. So bye until next time with Miss R.